our next rebel to, with a cause, actually, he's going to tell you about his cause, is Ashutosh Saxena. And he grew up in India. He went to IIT Kanpur. He came to Stanford, where he did his PhD with Andrew, who was here earlier today. He has done pioneering work in algorithms for perception. He's extremely well known for something he did during his dissertation called Make 3D, which was an algorithm for converting a single still photograph into a 3D representation. It was covered in the press and made into a website that's used by thousands of people. And then he applied it to obstacle avoidance for UAVs. He went on to develop a number of other algorithms in robotics for applying learning methods, and specifically grasping has been an area of focus for him. He's applied deep learning to grasping, applying rigorous methods like Gaussian process, latent, conditional random fields, as we saw in the paper that he has here. He has made a number of major important contributions, and I'm also particularly struck by something he's been doing lately, which is starting to incorporate crowdsourcing into robotics. And he has these beautiful examples where he has websites set up, where, and we saw an example here, where the crowd, the individuals online are invited to help out robots by reviewing video sequences and then annotating them and advising them, essentially building models from the data that's collected that will actually help robots to learn over time. And I think this idea of humans helping robots is just in its infancy and incredibly powerful. So he's now an assistant professor at Cornell and leads a big group there. He's also got a very exciting new idea that he's going to reveal today. So with that, please welcome Ashutosh.
Hi, thanks, Ken. Can everyone hear me? All right. So this is another anniversary for me. I started doing research in robotics exactly 10 years back when I joined Stanford. So I thought this would be a good time to announce my new work. I've been a machine learner from PhD times by profession. And I've been working in robot learning for different domains, perception, planning, and language. And today I'm going to talk about a new project that supposed to make a big progress in each of these areas. So just to recap, there are different kinds of robots. It's my talk, so I can categorize them into 3 categories, which I will call perception, planning, and language. And all these robots need to do these 3 basic skills. They need to have these 3 basic skills. For example, a self-driving car, you may need to talk to it. It needs to perceive this complicated environment and figure out decisions and plans on how to drive. And Julie just showed a few examples where in factories, people are working with robots. So they need to perceive using their sensors on what the people may be doing and plan accordingly. In another example that we are recently working on in the Tell Me Dave project, it's a household robot, and the person wants to talk to the robot to do certain things. In order to do these things, the robot has to solve really hard problems, which is to figure out from its sensor what are the things in the environment, listen to the person, get the context and the knowledge base of what is the environment and what is the person trying to tell the robot to do, and then plan its motion to perform these tasks. So let's take a step back and then just try to figure out that we as roboticists, how each of us in our problems try to train our robots. So some of us work in planning, some of us work in perception, and some of us work recently in language, and we have our own ways of training these systems. For example, in perception, there are really amazing research groups and software output from people such as Marshall Hebei, Dieter Fox, who has been working on 3D models, and my own research group, which has been labeling these 3D scenes and figuring out what is happening in a video and so on. There has been a lot of work in planning where we are trying to get the robots to do certain things, such as control this ball and put it into a box, or interaction with people in our recent Planet work, or Bagnall's work on teaching robots on how to drive and so on. So here people have to figure out their individual mode of training for doing that particular task. And more recently, there's a lot of work in this human-robot interaction through language, for example, by Stephanie Telek's, Maya Kakmuk's work, and my student Dipen Mishra's work on Tell Me Dave. So today's talk is going to be about the one fact, which I think we all agree. If we figure out a way to do all three of these tasks together, is going to be a big win. And let me take a very particular example of why that is so. So I bought this cup today before coming to the talk. I can call this cup a cup, and if I go online and search for images of this cup, I will get a tons of images. I can get a ton of 3D models. But in addition, if I touch this cup, I can get the 3D shape, which is a different property. For grasping and haptic people, I can actually feel how it feels to hold in my hands. I can in fact go to YouTube and figure out people who are using this cup for different purposes, such as drinking, measuring, or even throwing at people, and so on. I can even talk about this cup. I can describe in words how this cup is doing. I can do all these things, but the reality is that this cup is a single concept. And so far, in many of my previous work, I've been trying to work with vision researchers and 3D modeling people and language people who talk about this cup as if it's like 7 different things, not one single thing. There has been some recent amazing work that is trying to combine some of these concepts. But let me try to walk you through over the course of my previous 10 years projects on how I want to build a common representation that can build a strong knowledge base which we can use for perception, planning, and language, and do some amazing things. So I'm going to look at my 10 years back and talk about my next 3-5 years plan in the course of this talk. So let me start with a very basic example. How many people work here in grasping? Oh, half the crowd works here in grasping. That's cool. So let me just talk about grasping. So this is from my previous life in 2006. That was one of the first PhD projects. And here the problem was that we were given an image of a robot. So robot goes out into the world, looks at an object, and the goal is to grab that object out. This problem of grabbing a cup that was never seen by the robot before was an unsolved problem in robotics in 2006. And the challenge was that if you don't know the object, you don't have its 3D model, how the robot can figure out where to place its fingers and pick it up. So I took the very basic machine learning algorithm I knew at that point in time, which was actually a logistic classifier, which was just compute some features from this image, and the goal is to find a binary classifier, 0 or 1. This should be 1 where I want to grab the object, and this should be 0 at the other location. As simple as that. And then I gave it a lot of data, which was actually 10,000 or 15,000 images from a computer graphics database, which was easy to generate. It's fully labeled. So if I tell the computer that, hey, the pen could be grasped from here, martini grasped from here, and by looking at these other objects, the robot was able to figure out how to pick up this cup, which was really great, because then we applied it to a bunch of applications, and one of them was unloading items from a dishwasher, which got a lot of publicity, because it's very cool to have a robot that can unload items from a dishwasher. More recently, we have learned significant progress in these different machine learning algorithms. In the morning today, my advisor, Andrew Ng, showed some of his deep learning algorithms. So since last year, we have been trying to include some of the deep learning algorithms, and my student, Ian Lils, has been actually able to learn automatically which features are important for grasping. So you do not even need to design features for the logistic classifier. All you need to do is to give it a lot of images and a few examples of how to grab things. And it will learn these powerful representations that, hey, for an object like this is a neuron that fires, and this looks like a handle, so I should go ahead and grasp that object. So this is the first piece of information. I can talk about this cup in terms of how I want to grab it. And I can store this representation in the system. The problem is all of our robots in factories, in cars, in household don't see this single object separately. What they actually see is cup lying somewhere in this environment. So the next thing that I looked at was how can I capture this rich structure in the environment, the spatial distribution of objects, how they are arranged, in order to reason and build a better representation of what a cup is. So let me take an example. Here, the goal is to figure out where should I place the cup so that it is most relevant. But before I could do that, I need to get an understanding of the environment. So one thing we could do is divide the image into small pieces, such as this piece, and each of them I can make a node in an undirected graph. And the label of this graph would be what this object could be. So for example, this object could be a mug, or this object could be a chair or a jacket. These edges represents the spatial relations that we typically found in these in our situations. For example, a keyboard is usually found near the monitor, and laptop needs to be on the top of a table because that is how it is stable. You cannot have it hanging in the empty air. So this graph is a way to encode our knowledge about the physical properties into the environment. In fact, this particular algorithm is called conditional random field, and it was proposed by Lafferty et al. In 2001. And Kevin Murphy in 2003 had a really nice paper that applied it to labeling in 2D images. And in my own work, I proposed something called a Laplacian MRF, which is called Make 3D, in which you can take a single image and produce depths out of it, which can make the robots fly. Moving forward, when the RGBD sensors came out, our lab is the leading lab which has produced a software that can take 3D point clouds and produce labels out of them. The cool thing about this software is that in the same graph, we can encode a lot of information about appearance of an object, 3D shape of an object, object-object relations, object-part relations, and the algorithms that we have developed have very nice properties. They could be solved efficiently using graph cuts, and even in this big graph, they have half-integral guarantees. This software has been tested on multiple robots in a wide variety of environments. It has been running in robots and software in different companies, such as Qualcomm and some of the big search companies. So let us take a step back again and try to figure out what did we gain from this. What we gain from this is, after getting an understanding of how different objects relate to each other spatially, we gained a little bit more knowledge about this mug. Now we know that this mug is somehow related to other objects in the environment in a certain way. We got an understanding of not only about the 3D shape and appearance of this mug and how to grab it, but also how does it relate to other objects in the environment. One of the problems of building knowledge about this cup in this particular way is that we have been only adding knowledge to this graph in a way that is the only knowledge we are adding is the one that is visible. As Julie Shah described, and Maya Kakmak described, and Andrea Thomas's work has described, there is a lot of reasoning and hidden factors behind things happening in a certain way. And what we really need to add in this work is the ability to discover these latent factors that may not be immediately visible in the data, but we do need to model it. And the reason to learn these latent factors is that if we don't do this, the size of this graph becomes so big very fast. There are so many objects in the environment, and even if we have, let us say, 1,000 objects, and we need to model all these relations, the number of relations we need to model is order of 1,000 square, which is 1,000,000. So this graph just becomes very big. We need to do something about it. So motivated by many of the works in game theory and HRI community, we took a look at this image again. And then we realized that actually one of the hidden latent factors of using this environment is not because these keyboard and monitors are related to each other in a certain way, but the real reason behind it is that there is a person using these objects. And if we are able to learn by looking at images what these people do, what these people want, how do they behave kinematically, dynamically, and maybe even at a higher intent, we can build much powerful reasoning for these robots. Hello? Yeah, much powerful reasoning for these robots. And let me just quickly explain what this figure is doing. It's essentially trying to explain the existence of all these objects by modeling how humans are using them. And a particular visualization is this. This person is sitting here, and this is for the laptop screen. And if the robot is trying to figure out where the person may be sitting so that maybe it can help it out, it knows if the laptop is here, the person will be here. So it can just query the graph and get this information and do whatever it wants to do. So let us add this information back into this graph and try to have this additional information in which we can not only model humans, their kinematic and dynamic properties. And there's actually nice work by Emil Demerican, who has been building these muscle-based models of humans in a very detailed manner. And our recent work by Yun Jiang in the RSS, this RSS talk also talks about how to include those high-dimensional properties into the models. So now we have agents, their models. We can reason about objects. Now it becomes very easy to actually reason about and add more information to this graph. Let me quickly mention some of the algorithmic challenges that come up, which are actually not solved immediately in the machine learning community. One property about this graph is that as I keep on adding more information, we will have more and more nodes and edges into the graph. It's a non-parametric setting. The data keeps on coming in. I need to keep on adding nodes and edges into the graph. In fact, I don't even know the graph structure. It may keep on changing. As the new beliefs come in from all these kinds of different observations, the graph structure will keep on changing. So in previous work by Lafferty and Kevin Murphy et al., the assumption was that the graph structure is known. The specific problem was, given the undirected graph structure and some observations, let us find out the best possible labelings over this graph. But in this kind of work, when we are trying to deal with real robots in the real environments, we need to deal with latent factors. We need to deal with unknown structure of the graph, whose structure is actually changing as more data is arriving. So our work on infinite latent CRFs and the earlier version of it in ICML, we have built these algorithms that are non-parametric, semi-supervised algorithms that can, on the fly, change the graph structure as more data comes in, and we learn the distributions over these possible graph structures, which gives us the power to actually manage this big graph and information base in a very nice fashion. Actually, we have also done a lot of quantitative studies. We have tried it on variety of data sets, Cornell data sets, NYU data set, activity problems, different problems, and such kind of powerful modeling when we model these latent factors using humans and our new machine learning algorithms has given us consistent improvement over the state of the art in a variety of tasks. And in fact, this has become so easy if you use the right machine learning property of pushing in beliefs from different data sets. If we get a new data set, which is actually Hema's work, Hema Kopula's work, which was the best student paper last year, she was trying to model how humans act in the environment. So as I explained, this is a mug. If I can observe people doing things with it, and the robot can see how people are acting out in the environment, which is also what many HRI people do, because interacting with people or watching people is another way to learn about these things. If we get another piece of information, which is maybe person are moving, so in this case, if I know how to grab a mug, I can actually reason about how that mug may be used. So this is showing the trajectories modeled using Gaussian processes over a CRF, again, non-parametric graphical model settings. So I can take this information and push it into our knowledge graph. So now we can keep on building these powerful knowledge graphs as much as we want to. And this I just take the example of a cup, but we have been dealing with hundreds of different objects, and this is another example that we can keep on adding into the graph, and so on. Now, let us come back to the more interesting question of how we can actually use this graph for doing some of the things in robotics that we all want to do. So it's actually very reasonably simple problem. The building the graph is actually trying to push knowledge and beliefs and graph data into the graph. Querying is, and using it is all about query. You have to ask the right question. So for example, in this case, we were trying to have a robot help out a person. So in this case, a person is trying to pick up a pot and go to doing something that the robot does not know. But using our vision algorithms, we can parse it out. This is a simplification. We actually have more than 500 nodes in the graph. And we can query the graph about what are the possibilities. And we can use our conditional random field inference algorithms to figure out, given the possibilities, what are the most likely possibilities. So the most likely possibilities in this case, the person may be reaching to the fridge or putting it into the cabinet. We can query the graph again for what objects are there and how exactly the person may execute all of these motions. And this could allow the robots in different environments, such as self-driving cars, factory automation, home and office systems, to anticipate what people may be doing in the future. So if you see a kid trying to walk onto the road in New York City, unless the self-driving car is a New York City taxi cab, it should stop. Uh, um, and here's a video that actually we did it last year. Here it's showing it in action, where it's using the depth camera. It is observing what the people may be doing, and actually even before the person does it, our robots can anticipate pretty well 3 to 10 seconds into the future by querying the graph. And now these are the two top possibilities, and now it can put it back, the person can put it back or take it to the fridge, and whenever we want to. And this is the question we did not answer very well, which is an open question, which is how do you actually figure out when the robot should come in? Here we just said if the belief is so high, then take this particular action and go ahead with it. Although recently we have been building more powerful models of human intentions using Markov decision processes and so on. So let me take another example in the planning domain. Here the goal was to plan paths, and this is a mug, this is a thing, this is this egg container. If I use the standard geometric path planner and try to move this egg carton from point A to point B, I will come up with this red curve, which is not the right thing to do. Now someone can come in and say, hey, I have seen people do it this way, or I can put constraints in the planner. That is very easy. To clarify, the challenge of this work is not to build the right plans. The challenge of our work is to figure out how to learn what to ask the planner to do. We can observe, do human-robot studies in very specific ways, but what we really want to do is that whenever someone does that study, we push this knowledge into the graph, and whenever a planner requires it, we query the graph and figure out how to do it. So in this particular case, again, it's a graph query. Here, the graph is actually a trajectory waypoints based on Andrea Thomas's work, and we have already learned enough information about the different objects that we can actually figure out that this score, this graph in this setting should be the highest one by querying the graph. There's another interesting aspect of the work. So far I've been talking about how do we learn this graph, and it has been mostly in a visual setting, which is you go online, get the images, you observe the people using vision. This work is amazing in that we actually have a new setting in which the person actually believes something about the control or the planning trajectory is the right one, and the robot is trying to learn it, but the person is unable to express this directly to the robot. Expert demonstrations by people and communicating to the robot only works in very few situations. So for example, for flying the robot, I remember 8 years back, Andrew Ng and Peter Abel had to wait for this expert helicopter pilot to fly those, to demonstrate for them. They could not even fly those helicopters themselves, which works fine if you are able to find a helicopter pilot and pay him $200 an hour to fly that plane to train the robot 100 times or more. But in real life situations, it's really expensive to collect that data. So this work called coactive learning has been able to even take a very weak signal and learn from that. So even if you never demonstrate the optimal trajectory and you only improve in expectation using crowdsourcing, we can still have similar regret guarantees as in typical inverse reinforcement learning people do. And here's a quick application of how how we can actually push information from human interactions into the graph. So here, the robot did not know about how to use a knife properly. And then it did not, so that property was not there in the graph. And here the person is physically interacting with the robot, and this information, this incremental correction would be pushed into the graph in order to learn a better representation of how to plan things, what are the objects. And this correction can come in many forms. It could come as a Google search result. So in this case, the robot was shown 3 trajectories, either physically or online on our planet system. And all this information could be very useful for the robot to learn new things about the environment. So as you can see, it's an online learning system, and every single update is improving the system. The cool thing is that when it is a new environment, so remember the person was front, now it is in different sides, there are a lot more objects, it can still query the graph to come up with an interesting trajectory. Let me finally show you one more example very quickly called the language. So because we have this graph, we can actually relate this natural language text to this image and parse and create sentences, because concept in text to images to symbols to actions to observations are all one thing. It's not 7 mugs, it's really 1 mug that we want to learn about. And here is a video that we showed yesterday about this person verbally asking the robot, and the robot will try to parse what the person has said, query the graph, come up with a plan. Knowing enough about the environment, it can hopefully do some of these things, which is adding coffee, then scooping things, using grasping to pick up our scooper. There are other interesting challenges, like haptics is one big challenge. We have not been able to push properly into the graph so far, because the challenges in robotics are significant. We get so much varied data, it's extremely hard to do all these things and push these things into the model. So this thing is ready. And again, we have the one thing I should like to emphasize is that these are not one-off demos. What I am really a big fan of, coming from the machine learning community, is to build these different data sets or use other people's data sets. And I have never done a single evaluation with less than 10 objects and less than 100 data points. That's a no. I fire the PhD students if they attempt to write a paper with less than that number of experiments. And we have seen consistent improvements. But now let me take a step back and talk about what I'm going to do in the next few years. So this graph was an example of a single cup. One of the real challenges is, how do we scale this up? So I asked my colleagues, and then I went to the respective communities to talk to people. So one first very famous thing that came to mind is the NEL, Never-Ending Language Learner. It has been learning since 2010, and people have actually figured out how to parse a large amount of billions of text on the internet and build very powerful representation. Watson has been doing that for a long time, and it actually won Jeopardy. In the talk today, this Google has been parsing YouTube videos because, well, they have a lot of videos, and just using a flat representation and using a deep learning algorithm, they can build very interesting systems in a very scalable way. In our community, it's actually much more challenging in robotics, because while different people have to only deal with one particular data, we as roboticists have to deal with all kinds of data, haptics, motion, humans, vision, and so on. It's really hard to put it together. So this is actually very challenging. And that is the purpose of this project that I thought about, and we just formally started it a month back. And the goal is that in this RoboBrain, which is actually a big knowledge graph, it's a collaboration between Cornell, Stanford, Berkeley, and Brown currently. We should be able to push all the information, all the data into the internet that is available. ImageNet has 14 million images. Yahoo Images at 1.4 billion images. 3D Warehouse, 2 million. All the contemporary works which are looking at ways of how to scale the data up, how to communicate between robots, how to build these online tools, and Planet, led by Jenkins and Goldberg in these respective efforts. They can help us to build systems that can push knowledge into this graph. And our recent work on Tell Me Dave that can push WordNet and other information into this graph. Let me just finish with these challenges, which is there are some known challenges that we know how to handle. We know how to deal with larger scale databases. We all use Facebook, we all use Twitter, we all use Google. And if we can get the right people, we can get this data set. In fact, I have hired one of the leading people who build the streaming services for one of the famous movie watching websites online, and we know how to do this. Learning algorithms are a big challenge. We want to give them the data set so that if we push this information into the graph, machine learning people can work on different things instead of building better and better classifiers. Another open challenge is how we can incorporate new pieces of information. And finally, how we can use this graph, this RoboBrain graph, and embody it into different robots for doing different things. Thank you. This was a work of a lot of students and professors and some of the industry people. Thank you.